Our first speaker is Balazs Szegedy, who will help us think about AI from a completely new angle.
His talk, How to Think About Artificial Intelligence, explores the mathematical foundations that shape how we understand and what we can truly expect from AI. So let's welcome to the stage Balazs Szegedy.
So, thank you very much for this very kind invitation. So, I think that you agree with me that one of the most interesting developments in the last 10 years, in the last decade, is that AI system became surreally powerful. And actually, we can now talk about an AI revolution. It's quite new for many of us. I think it's very important to understand what AI is, how to think about it. Let me give you an analogy, like when computers were new, like as new as AI now. In the 80s, people who learned about computer viruses, some people were afraid that they can catch those viruses. So this is because they didn't know how to think about computers. So I think there is a similar thing today that there are many misunderstandings about AI, and it's very important to clarify certain concepts. But this talk is a little bit, and I apologize, it's not for like, it's a little bit for experts, so it will contain some mathematics. I hope that you don't fall asleep when these mathematical parts come. If you lose attention, then the next slide will jump and you can, again, reconnect to the talk. So basically, the goal of this talk is to give you a high-level picture of how we researchers and AI developers see artificial intelligence. What are some of the key concepts which drive our work, and how we think about it. It won't be complete. It will be actually very, very far from being complete. So you may complain that I didn't mention this or that. But in half an hour, I cannot squeeze too much. So I apologize for that. OK, so let me start with a general view on AI. We talk about AI a lot. But AI is a very, very diverse, very big subject. It has been around for many decades. And the part of AI which drives this fantastic revolution that we see now is actually a very small part of this huge landscape, what we call AI, artificial intelligence. Actually, this picture is just a small part of this taxonomy tree of concepts relating to AI. So it's more like just an illustration. I just wanted you to see that the part which is highlighted here on the slide with blue is the one which is responsible for the AI revolution. And the rest is not really, not so much. So in other words, we developed over decades many different ideas how to approach artificial intelligence. And it turns out that this particular approach, which is based on neural networks called deep learning, is the one which is now doing this revolution for us. So also let me mention that deep learning belongs to the subject of machine learning. And machine learning has many other branches, again, like other models based on physics, statistical physics, Boltzmann machines, and so on. I won't talk about those. I just wanted to mention them, that they contributed to our understanding of AI a lot. But now we focus on deep learning. And also, there are learning paradigms, which these are important words that you may hear when you study deep learning and machine learning in general. There is reinforcement learning. There is unsupervised learning. There is supervised learning. So basically, if I want to describe this, what they are, supervised learning is when a kid is learning stuff and the parent tells the kid that this is a giraffe, this is a bear. And so this is supervised learning. Unsupervised learning is when the kid just explores the environment and just understands the structure of it. And so reinforcement learning is when there is a reward, which is typically delayed, and the agent, again, explores an environment, but there is a reward which is delayed, and it needs to navigate in this environment. So these are some learning styles, learning paradigms. But then there is deep learning itself, which is based on various models, architectures, and let's talk a little bit more about that. So deep learning, as I mentioned, is based on artificial neural networks. And these structures are motivated by the human brain itself. These are mathematical functions that we model on computers. Recall that, I mean, if you have learned that the human brain has the neurons, we have many, many such neurons. They are connected to each other. They collect signals from other neurons through these connections. And if they have, I mean, from time to time, they just send a signal. And then the signals are like a big drum concert. Imagine that each neuron is a drum, like tuck, tuck, tuck. It can give a signal. And our brain, if you look at how it works, it's like an enormous concert where there are involving billions of drums. And there are synchronized patterns and all kinds of things. So this is the brain. Artificial neural networks are a bit different, but they are highly motivated by the brain. And this is less like a drum concert because the signals that they send are more continuous. But we get there soon. But I talked about AI revolution, so I think it's good to just look at some of the developments to understand this revolution. So the first big results in AI came in computer vision, in the subject of computer vision. AlexNet was one of the breakthroughs on this ImageNet, and that was the first very promising computer vision system. My brother, Christian Szegedy, I will also talk about him later. He was at the Google that time, and he came up with the Inception network, which was a state-of-the-art network. And he became very famous with that. Then there is the residual networks. So all of these systems revolutionized image recognition, computer vision. And it's very interesting to know that I'm sure that you have heard about AlphaGo, this computer system which in 2016 could beat Lee Sedol, who was considered to be one of the best, if not the best, Go player. And people in the Go community didn't really expect that. Actually, people expected that the computer system which will beat an expert human player will be like 50 years away. So a revolution is when things happen much, much sooner than people predict and expect. So that was definitely a kind of a moment when you realize that, this is a revolution, like things happen much, much sooner. So yes, this AlphaGo could beat Lee Sedol in Go, and this was based on the results in computer visions, partially on computer visions, the convolutional neural networks, and partially on other developments in reinforcement learning, and also some regularization techniques, partially again developed by my brother Christian. So this was computer vision. So computers first learned how to see, but then later, a few years later, they also learned how to talk. So transformers appeared. This is another very important architecture for deep learning. There is this very interesting paper with the catchy title, "Attention is all you need." And so this introduced a very novel architecture which was capable of reproducing human language. I don't really have time, since I see that time is going fast, to talk about these tiny details of this thing, but later, new developments came. Also, how to generate pictures. For example, these diffusion models were very efficient at generating pictures. So if you ask ChatGPT to produce a picture of a Pokemon playing water polo, then this is typically using a diffusion model or something similar. So all these things are very recent. You can have a large language model which was first trained on general data, and you can then make it more specific by further training, all kinds of things, but I don't go into the details of that. So because I'm a mathematician, I like to at least give you an idea how these AI systems work, why they work. So for that, I would like to talk about this very basic mathematical concept of a function. A function is just a machine which takes in an input and then produces some output. So for example, here is the picture of a machine. It takes in a number, multiplies by 2, and then adds 3. So if you, for example, 1 goes in, then 5 comes out. So that's a machine. Another one is which squares a number. But actually, so these are functions from high school. But there are more complicated functions, even with numbers. There are functions which take in 2 numbers. So a pair of numbers is the input, x and y, and the output is a single number, which is the sum of these 2 numbers. So this is addition itself as a function. So I just wanted to tell you that basic mathematical operations like addition, multiplication can be regarded as a single function if you look at them this way. Or a function doesn't necessarily have to take in a number. It can take in a shape and then tell the area of it. Anything which transforms something to something is a function. So it's a very general concept. Almost everything can be viewed as a function, if you like. I mean, many of you are programmers. It's not a miracle for you. Obviously, in programming, you have functions. A chess engine which plays chess or Go is a function. The state of the game is the input, and the next move is the output. That's a function. Physical reality may be considered a function, like this current state of the physical reality is the input, and what happens next is the output in some sense. I mean, you can elaborate on that. So it's a very general concept. But here is the interesting thing. You can have very, very simple functions and then compose them. You can imagine that visually. Here is a machine. Something goes in, something comes out. The next machine takes what comes out from the first machine, takes it as an input, and you compose them. Also, imagine that you have 2 machines. They produce some number, so you have 2 numbers, and there is one machine which takes in these 2 numbers as a single input and then produces something. You can actually have a huge network of functions, very simple functions, and then this huge network of functions, which is a composition of all of those, is a very complicated function. So this is exactly how computers work. You have these very simple logical operations, and you compose a large number of these simple functions, and suddenly you end up with something complicated. Now, this is exactly how neural networks work. There is some very simple core function, but you compose a network of these simple functions, and then you end up with a large, complicated function. Now, there is a key difference between ordinary computers and neural networks, even though neural networks are typically simulated on computers. But maybe later there will be special hardware. Already there is now special hardware which can do that directly. But now you simulate them on computers. But the thing is that here, like in ordinary computers, these functions are typically discrete. That's a term from mathematics, Boolean. They either give 0 or 1. In neural networks, the functions take in real numbers or even multiple real numbers, and output a real number. And so that's one difference. Looks like a small difference, but actually it's a major difference. And the other difference is that imagine that each function has some, your machine can be tuned with some potmeters, and then you can tune the behavior of the function. So you can mute the function continuously. And this is, again, a very important thing for artificial neural networks, that you can have this large network of functions. These are continuous functions, and then you can slightly change the behavior. And this is where the whole machine learning starts, actually, if you just consider this. But to do mathematics for these structures, you need to use differential calculus, which was developed by Isaac Newton and independently by Leibniz. It's a very powerful thing. This is the mathematics of tiny changes. When you have a system and you do an almost infinite, it's an almost zero change, but very, very tiny change, what happens? So there is a mathematics of that, which is very useful in physics, very useful in machine learning. So what is this simple function which in artificial intelligence plays the major role? This simple function is what we call a single artificial neuron. It just takes in a bunch of numbers, maybe 10 numbers or 5 numbers, so that's the input. And it adds them together, like my addition machine. But there is a small tweak that in this addition, don't be scared by this summation formula there. This addition, you can have some weight. So for example, 2 numbers comes in, 1 and 2, but the neuron have some internal weights, and you multiply 1 with maybe 10, and then adds 5 times the other number. So these weights are properties of the neuron, of the function itself. These are the weights that you can tune when you want to change the behavior of the function. And at the end of this, there is a finishing touch to the result of this simple formula. You apply this function. You apply some function. Typically, one of the most popular one is just this function, which for positive numbers, it just gives you back the number, and for negative numbers, it gives you 0. So there are these tunable parameters, the WIs, and then you compose many of these functions, and then that's a neural network. Again, time is does not allow me to go very deep into this side. Good for you, because it has some mathematics. So I just go quickly through it. So basically, when you train a neural network, you start with a randomized initial setting for this function. So what these functions do that you compose, the neurons are randomly set at the beginning, and what the whole neural network does is some crazy thing. It doesn't make sense at all. It's not useful. What makes it useful is that there is a training process, and the training process it's running on the computer, which uses differential calculus to find small changes in the parameters governing these little functions. So it uses these changes to improve continuously the performance of this function. And it grows smarter and smarter by itself, by just this simple mathematics and the training process. So basically what you program, or I program, if I want to create such a neural network, I actually program the training algorithm. This is what I create. And then the training algorithm, when I let it run on my computer, it produces a trained neural network. And then this trained neural network can do certain things. So let me jump a little bit back and forth between slides, because I want to definitely tell you an immediate philosophical implication of that. So that's the first more like very high-level philosophical thing that I want to stress. So artificial intelligence, at least in this deep learning form, is substantially different from programming, from original programming. In original classical programming, we build something that performs a task. We write a computer program, and then this computer program, I wrote it, so I know exactly what it does, and it does something meaningful. That's programming. I love programming, actually. It's very addictive. Because you build a machine which then does nice things, right? It's really cool. In deep learning, you are one step further from the output. You build something that performs a task. So you don't directly build this neural network that will do nice things for you. You build what you program, as I mentioned, is a training algorithm. And then that training algorithm builds you the neural network. That is actually an analog of the computer program, more like a fuzzy version of a computer program. It's, again, just composition of simple functions, like a computer architecture. And that this grown thing will do great things for you. But you are one meta level further from this. It's almost like you just plant the seed and it grows itself. It evolves like we evolved. In billions of years, your neural network, which starts completely stupid, evolves slowly, and you are not doing it. This is done by this iterative algorithm, the training algorithm. It grows smarter and smarter and smarter, and then it is capable of doing things. But because of that, we understand it much less, why it does certain things. And that's a problem for us. This is called the black box type behavior because we don't quite understand. I mean, it has billions of neurons maybe, and it performs certain tasks, but why, how, this is a mystery. And it actually, when we want to apply neural networks in real life, that's actually a problem. Because, for example, if there is a self-driving car using neural networks, it hits somebody, then we want to know why it hit the person. And this why is hidden in the billions of neurons, which do something. So that's actually a big topic. Sorry for jumping between the slides because of time. I try to optimize the talk. So there is a whole subject. It's called interpretability, which is the subject of looking into this black box, making it a little bit more transparent, turning a black box into a gray box. So explaining why AI made a decision. And there are two approaches. Actually, there are many approaches, but let me mention two approaches. One approach is to train the neural network in a way, to create a neural network which we understand a little bit better. That's one direction to go. Another direction to go is to, for any model, try to explain why it does something. You can associate decision trees maybe with these neural networks. That won't be very precise, by the way. This will be more like just an approximation of what the neural network does. So here is an example about this car hitting a person, but I don't have time for that. I want to consider two more topics in this time I have. One topic is the data dependence of AI. The data dependence is actually a problem because these large language models are already trained on the whole body of stuff that we produced, like written material. And we are running out of data. So how do these systems get smarter? So have we hit some wall because of we are already training these systems on everything that we produced? And so we reached a certain intelligence, but can it be smarter? So AI is data hungry. I am less pessimistic or optimistic, if you like, about this. I think it's not a real problem that we are running out of data. So just a proof of concept that we don't need data for AI is, or we need data but in a different form, is AlphaGo, exactly, the system AlphaGo. AlphaGo has a version, AlphaGo 0, which is absolutely not using any human-created Go play. So it's not learning on Go games which humans played. It does self-playing, a lot of self-playing. And from those self-plays, it produces a data set, a growing data set, and it learns on it. And then it again plays with the new knowledge. So AI can actually produce its own data, feed it back into itself. So it's almost like a self-reinforcing cycle. Also, if we have a better architecture but the same data, maybe it will learn smarter things. That's another thing. So even though we are already using almost the whole human-produced data, a better architecture may get more intelligent. So what I want to point out is this. So can AI surpass humans? Well, there is this myth that AI can't beat humans because it only copies human data. It's as far from the truth as possible. As I mentioned, AlphaZero is a counterexample. So basically, I think, but actually, it also is it is a challenge how to do that in every single case. So I think producing synthetic data and then learning on that synthetic data, so improving the AI, and again finding even better ways of producing synthetic data and so on, and iterating this, we can actually surpass human intelligence. And one way of doing that is it comes from formal reasoning, where the rules of mathematics are fixed, like the rules of Go. So if you consider the rules of mathematics as a fixed system, and then you play games in it, but this is how you would train a system which can do proofs in mathematics. That's just one example. Then you can, whatever the AI produces, another system can check whether this is a correct proof, and then based on that, it can produce new learning data and so on. So it can somehow improve itself without any human knowledge. But this is just one example. You can, another is, I'm just daydreaming. Maybe you can create a simulation of reality where you can, inside this simulation, you can produce even more learning data, and then you can learn on that and so on. And then based on that, you can improve the simulation. So whatever, I mean, it's up to your fantasy. I think we already see examples where human data is not needed, and in the future, probably it will be less needed, and that's my prediction, but I cannot tell right now. Okay, so that was one very interesting topic. Another very interesting topic is about the weaknesses. I have talked about the strengths of AI, how good it is on certain visual tasks and language models, and maybe it will be very good with formal reasoning. There are certain problems with AI, and let me mention one, which is one of my favorites because it was produced by my brother Christian Szegedy, who was, by the way, in the founding team of xAI together with Elon Musk. And so the observation in this paper is that you can trick AI, so very simple, in a very disturbing way, actually. So computer vision is very good. I mentioned that it often surpasses human level, and obviously such a neural network can recognize that on the left-hand side there is a pig. But you can add, if you, I mean, in a mathematical way, you can create certain tricky noises that you add to this picture, but with a very, very small, just a very small intensity, you add this noise to the picture, and visually you cannot really distinguish the two pictures. You added a tiny noise. And then the AI, the neural network, will see this new picture as an airliner, although it's still a pig, right? So that's a problem. You have to be evil. I mean, if you just add a random noise, it won't do that. You have to design a specific targeted noise. And so that's the thing, that it typically does not happen. But if there is an evil person who wants to trick the AI, it can trick the AI. Obviously, there are certain defenses against this, and this is a huge research area. I'm not going to go into the details. You can do all kinds of, you can prepare, during the training process, you can prepare the AI for this type of adversarial attacks. These are called adversarial examples. And so, fortunately, this problem was caught very early on, and now the researchers are working on how to fix this. So there are problems with AI. AI is not perfect. It makes mistakes. It operates with probabilities. Probability, in fact, it's a very, very key concept in AI. Again, it belongs to the major concepts related to AI. So to me, some of the major concepts related to AI are generalization, because you train the AI on a data set and then it can generalize to unseen data, which is a miracle itself. I call it the miracle of generalization. We don't quite understand why it happens. I mean, we do have some ideas. It's a miracle, actually, that it works. Simplicity plays an important role in AI because it's related to this Occam-Razor paradigm that AI works, AI can generalize because it tries to find somehow the simplest way of extrapolating a certain data set. And so simplicity and generalizations are connected. And another very important feature of AI is that it works with probabilities. It gives you a sure answer. It gives you a probability distribution of possible answers. And then you can select the most probable answer. But this probabilistic nature also makes it prone to making certain mistakes. And so one has to be careful with all of these things. So AI is not perfect. In fact, it never will be perfect. There is this no free lunch paradigm, I didn't talk about that AI cannot be perfect. If it cannot be good on all possible tasks at the same time. There is always a cost that you have to pay if it becomes very good at some task. But anyways, it can be. But humans are not perfect either. So it's in this sense, it's similar to humans, but it can be very, very precise, maybe much, much, much better than humans. So let's see what will happen in the next 5 or 10 years. Thank you very much.
Thank you very much. Thank you, Balazs. It was a great presentation. We have 3 to 5 minutes still for questions. So in the audience, if anyone has a question to Balazs, then please raise your hand and I will go and bring the microphone to you, okay? Any questions? Oh, there is a question at the corner.
I would like to ask, what is your opinion about the human in the loop, which is very important when you are using actually the artificial intelligence. I mean that without the human in the loop, in real artificial intelligence, chatbots, for example.
May I give you a mic? Yeah, just to
approximation to a factual understanding, it won't work generally. It is related to the question whether there is a artificial general intelligence is possible at all, which is the kind of question that a lot of people are telling, like Sam Altman, that it will come. But because in the practical usage, it seems to me that the human in the loop is essential to make a closer, let's say, answer when you are prompting the LLM. Okay? So what is your opinion, actually?
My opinion
from this
is,
point of view. Thank you.
My opinion, thank you very much for this question. It's obviously a question that it is very important question, and many people would ask this question. I think our role in this loop is that we have to do it responsibly. So we have to create AI which serves us. Obviously, that's our role in the loop. So we have to be selfish in this sense. We have to look at our own interests and not let AI to grow on our head. So that's our role. We have to be alert. But philosophically, unfortunately, and that was the positive side of my answer, philosophically looking, I don't think that humans are actually needed in the loop after a while. I mean, right now, they are needed. Humans are needed. But keep in mind that the human brain is also a neural network. So once you have a human level, a new artificial intelligence which passes the Turing test, so you cannot really distinguish it from a human, then you can just use that instead of the humans, and that will replace the humans in the loop, and then you can make the whole system self-sustaining. So that will happen probably. It's almost inevitable. Our duty, our responsibility is that we still keep an eye on the whole process, and we make sure that it serves us.
Thank you. Maybe one more question, and then we can move.
Yeah, well, my question is about the abilities that you mentioned that AI can suppress human abilities, right? There is an argument about this that they will be bounded all the time by the data that we have. I mean, they don't have this counterfactual abilities. They cannot think of something which they don't know, basically. And another question about it is regarding your last point when you mentioned that we have to keep an eye. So if an AI is on the level of human intelligence level, we cannot keep an eye anymore. I mean, it will be smarter than being observed. So how do you solve that?
Tough question, obviously. The second one, so the first one is that it cannot think about something that it does not know. I would debate this. So it can, I mean, but the question that we should ask is, okay, but how do we know things? The way how we know things is that we observe the environment, and we observe. Suddenly, we observe certain things and form abstract concepts. Again, but my answer is similar to the previous answer, is that the human brain is also a neural network. So why could not these systems do the same thing and create new knowledge? By observing the world and suddenly understand certain patterns, and then that's new knowledge already. And in fact, this is provable what happens. It's a very interesting, there is a very interesting phenomenon in machine learning when it's almost like a phase transition. I wanted to talk about that when these language models or other AI systems learn on large data set, there is a phase of memorizations where they memorize individual examples, and then suddenly there is a knowledge appears. It's almost like a phase transition, and then it reaches a new state when it has a general understanding of things. And it's a fascinating thing. One manifestation of this phenomenon is called grokking, if you want to look it up. So knowledge can be created without humans. So the second, your second question is very, very tough, obviously, because I think that AI can be so intelligent that it will be like more like it will be related to humans similarly as ants. We are the ants, and the humans is the artificial intelligence. An ant, if you look at an ant, how much does it understand our concepts of philosophy, differential calculus, and everything? Nothing, basically. And now if there is a system which is exactly that much more intelligent than us, we won't even understand the most basic concepts of it. And so how can we control it? Well, I don't know, but probably what we can do is that we build in certain safety features that it at least doesn't harm us. And at least we have to set the rules very carefully. But this is something we should think about a lot. Thank you.
Thank you very much, Balazs, again. And thanks for helping us stretching our minds and see AI from a whole new angle. Let's give another round of applause for Balazs.
Thank you.